So in this we are discussing matrices, SAQs, exercise 3B, section 3, first problem, very important. If A is equal to 3 minus 4, 1 minus 1, then show that a to the power of n is equal to 1 plus 2n minus 4n, n 1 minus 2n for any integer n is greater than or equal to 1. So by using mathematical induction. So here, given that first we have to take that, given that the matrix A is equal to, so 3 minus 4, 1 minus 1. See, by using the mathematical induction, the process is, first you have to take that, let S of n be the statement that, so a to the power of n is equal to, so 1 plus 2n and minus 4n, so here n 1 minus 2n. So which is only the S of n, so therefore put n is equal to 1, here, so therefore S of 1 is equal to a to the power of 1, which is equal to, we get here 1 plus 2 into 1 and here minus 4 into 1, here 1 and 1 minus 2 into 1, n is replaced by 1, so finally we get which is equal to a to the power of 1, that is a, which is equal to 1 plus 2, that is 3, so minus 4, here 1 minus 2, that is minus 1, we get the same matrix A only here. So therefore we can write S of 1 is true. So next, this is step 1 here. In the step 1 we have to take that, put n is equal to 1 and substitute n is 1 here, we get A is equal to same matrix. Next, in the step 2 we have to take that, so let S of n be the step 2, S of n is also true for some n is equal to k. So assume that S of n is true for some n is equal to k. So now that is S of k is equal to a to the power of k is equal to here, so n is replaced by k, that is 1 plus 2k minus 4k and k 1 minus 2k. So see here, this is the S of k. Now what we have to do in the step 3? So in the step 3 we have to prove that S of n, we have to prove that S of n is also true for some n is equal to k plus 1. So now what we have to do? So to prove that the statement is true for n is equal to k plus 1 also, consider S of k plus 1 which is equal to, so S of k plus 1 means what? A to the power of k plus 1, so which is also is equal to, a to the power of k plus 1 can be written as a to the power of k into a power 1. So now which is nothing but, so a to the power of k into a, so this is S of k plus 1. Now S of k plus 1 is equal to, we have a to the power of k is, the matrix is 1 plus 2k minus 4k, k 1 minus 2k, and matrix A is 3 minus 4, 1 minus 1. Now multiplying both the matrices here, first row, first column, if you multiply, so 1 plus 2k into 3 and plus minus 4k into 1, and immediately first row, second column, if you multiply 1 plus 2k into minus 4 and plus, so here minus 4k minus 4k into minus 1. So then here, so second row, first column multiplying k into 3 plus 1 minus 2k into 1. So here k into my second row, second column multiplying k into minus 4 and plus 1 minus 2k into minus 1. 1 minus 2k into minus 1. So now which is equal to, if you multiply that, we get here 3 plus 6k and plus into minus is minus 4k, and here minus 4 minus 8k, and here minus into minus is plus 4k. So next here 3k, k into 3, and here plus 1 minus 2k. So here minus 4k, and if you multiply with minus, this is minus 1 and plus 2k. See further what we get here. So 3 plus 2k, this is 3 plus 2k, and here minus 4 minus 8k plus 4k, that is minus 4 minus 4k, and here so we get 3k minus 2k, that is k, so we can write k plus 1, and here minus 1 and minus 4k plus 2k, so that is minus 1 minus 2k, this is minus 2k. See, our aim is what every term must be, we have to prove in terms of k plus 1. So that's why here, which is equal to, this 3 is writing as 1 plus 2 plus 2k, and here minus 4 is taking common, minus 4 into, we get 1 plus k or k plus 1, both are same. Here k plus 1, and here minus 1 writing as 1 minus 2. See, minus 1 is nothing but 1 minus 2, and minus 2k is writing as it is. So now which is equal to, we get, so here 1 plus, if you take 2 common here, 2 into k plus 1, and here minus 4 into k plus 1, minus 4 into k plus 1, and here k plus 1. So here if you take minus 2 common, we get, so 1 minus 2 into 1 plus k or k plus 1. 1 minus 2 into, so k plus 1. So see, observe here in the S of k, wherever k is there we get the k plus 1. So 1 plus 2 into k plus 1 minus 4 into k plus 1, k plus 1, and 1 minus 2 into k plus 1. So therefore clearly we can write that S of k plus 1 is also true. S of k plus 1 is also true. So therefore by the principle of finite mathematical induction, S of n is true. S of n is true for all positive integer. So n is greater than or equal to 1. So that's why like this we can prove the solution.